Nobody else? Okay. Okay, so we're gonna just finish up a little bit with chapter 5 and finish up the worksheet that you have, which is entitled Orbits. And we had just done, if I remember correctly, parts A and B on the worksheet of problem 1. And I guess just to summarize what we did on Friday, we talked about the historical perspective of the view of what's in the universe, our place in the universe, what's at the center of the universe, if there is a center. And then we talked about Newton's law of gravitation and some interesting problems. Once we did a simple problem having to do with how to use the formula, we discussed how do you know what something like the mass of the Earth is, or the mass of Jupiter, or any other planet? If you look in the back of your book, you'll see numbers for all those. And the basic method is you watch something orbit around it. Draw a free body diagram and do F net equals ma, and you can figure out what the mass is from that, just by knowing the period and the radius of the orbit. We also talked about Cavendish's experiment, which determined what capital G was in Newton's law of gravitation, which was revolutionary at the time because Newton didn't know what capital G was. He just knew it was a constant. And that allowed Cavendish to actually compute what the mass of Earth was. So that was kind of interesting. The last couple of things we want to talk about, again, we're sort of talking about gravity and the concept of orbits here. How fast, if something's at a certain radius away from an object of a certain mass, so here I'm imagining Earth at the center of this circular orbit, and here's an object of mass m out at a radius r, how fast does it have to be going to maintain that orbit? And, you know, just because we've done some work like this, what do you think would be our approach? What do you think might bear fruit in terms of telling us how to calculate what v is? Where's that v going to come from? Yeah, that sounds like that speed at the top of a loop to not fall off, although it's kind of a different problem there because then, it's not like the same thing's happening as you go around the loop. Their gravity down and something different is happening at the top than the side. So that was a little bit of a different problem, but yeah, Arthur. A equals v squared over r. So the v is going to come into v squared over r. We're going to use a in F net equals ma. So we need a free body diagram first, right? At this instant in time, we want a free body diagram. And I think I've got this in here. So I'll just go through on the slides there. It's a pretty easy free body diagram. There's only one force acting on this thing as it orbits, and it's the gravitational force from Earth or whatever this body is here. And so anytime there's just one arrow going off of it, and I want to, of course, as always, when something's in uniform circular motion, you want to take your axis direction toward the center of the circle. So those are the axes I'm going to choose there. We won't use the perpendicular axes. So sum of the force x components equals max, and ax is v squared over r. That's where it's going to come from. And of course, the force we're talking about is due to Newton's universal gravitational force. So we just plug that in on the left side. That's the only force with a non-zero x component. That's the mass in the free body diagram, the mass of the thing that's orbiting, times v squared over r. And what I want you to do now is use that kind of idea to solve problem 1c, and we can throw in 1d at the same time. Again, anybody else who's doesn't have this sheet? There are a number of people who were gone on Friday. So here's a person of a given mass, and they're so far from the center of Earth. and you're given the mass of Earth at the top left of this, and we want to find out what their speed is at the radius they're orbiting Earth at in a circular orbit. Okay, maybe some of you have calculated, but let's just go through together here at the board. Of course, there are some cancellations that take place. One is, that's kind of interesting, it doesn't matter what the mass of the object is that's doing the orbiting, that mass cancels out. So apparently, if you have a little piece of styrofoam or a big lead ball or a car, whatever, it doesn't matter the mass, it has to be going at the same speed to be going in a circle at that particular radius. The other thing that cancels is I could multiply both sides by r, and that would get rid of that r and one of these powers of r in the denominator. So I'm just left with a 1 over r on the left-hand side. And if you really wanted to solve, I don't recommend memorizing this formula because you want to conserve memorization space in your brain. At least if you're a pre-health, pre-medical student, you need all the memorization space you can get. But I'm not very good at memorizing, so it's sort of one step away from F net equals ma. Why make it more complicated? But here's a formula that we could write. V is equal to the square root, if I just take the square root of both sides, of GME over R. So I plug in capital G, that's 6.67 times 10 to the minus 11 in SI units, look up my mass of the Earth, put in the R that was given. You always have to be careful when you're looking at that homework. Make sure when you're calculating R in here that they didn't give you the altitude above Earth's surface, in which case you would have to add on the radius of the Earth to get that R. But in this case, it really was measured to the center of the Earth. When you plug in those numbers, I get V equals 7720 meters per second. Meters per second. So not the most interesting number, but it's pretty fast. Things that are orbiting Earth are going pretty fast. The closer to Earth they get, the faster they have to go. And this is not terribly far from the surface of Earth. If you compare the radius that's given to the radius of Earth, they're not that far apart. So this is not too far from the surface of Earth, presumably far enough to be above the atmosphere so it doesn't slow down. Okay, that was C. Any questions on that? Yeah. So let's go back to the question was about the free body diagram and applying F net equals ma. So let's go back here. Here's my free body diagram is literally just that mass, m, and the only force on it is the gravitational force due to Earth. So this I might label as F from Earth. Gravitational force from Earth going in that direction. And we chose, as always, plus x toward the center of the circle, right? This thing is going around Earth here, and that's supposed to be the direction toward the center of circle. So what is the strength of the gravitational force from Earth? Well, Newton tells us that anytime we have two objects pulling on each other, and the distance between their centers is r, the magnitude of the force on this, of this one on this one, and of this one on this one, Newton's third law says they have to be the same, so there's only one force to talk about, is G times the one mass times the other mass divided by the square of the distances between the centers. So that is just the x component. This right here is the x component of this force, and it's all along x. So yeah.
Solve for A and B for acceleration in B, so couldn't we just use the acceleration map?
You certainly could. I had just totally forgotten what we did in B. Yes, given that we'd already done that, which was last Friday, so I'd just done it. But yes, you could have just set A equal to B squared over R. Yeah, but in a generic homework problem, you probably won't have done that right ahead of time, but that's one shortcut there. D, if the person stands on a scale, what would the scale reading in newtons be registered on the scale? Yes, 0 newtons. Yes, I mean, the idea is, look, we've already determined that this force is just the right force to cause just the right acceleration to move in this circle. Let's suppose they're standing on the scale, or trying to stand on the scale with the scale in between them and Earth, so that they would be pushing down on the scale and the scale is pushing up on them in that direction. If there's any force from the scale, it's going to upset that balance, right? And you wouldn't be at the right, you wouldn't have exactly the right force on you to move in exactly a circle there. And of course, if you did push on the scale, you would just shove it away from you and you wouldn't be able to stay standing on it, right? As soon as you applied a little force, you would start floating apart inside the space station there. So the answer is 0 newtons, because we already sort of made the assumption that just the gravitational force is enough to keep it going in a perfect circle. So if you're staying in that circle, there can't be any other forces. All right. Other questions on that one? Let me click forward on this a little bit. Yes, we did that. And again, I don't recommend memorizing that formula. That's a formula you'll probably see boxed in the book. But it's just another formula that's like one step away from F equals ma. So since we're so good at F equals ma, we may as well not do it. Okay, that sort of begs the question, well, suppose I'm out here at this radius and I'm going a little bit slower, or I was going at the right speed and someone slows me down for a second. Or there's a rocket I blast out in front of me that slows me down. What's going to happen? I'm still out at this radius, but I'm not going at the right speed. What would happen then? Yeah. You would lose the circular motion. And in fact, we know, from our very brief description of Kepler, Kepler is saying the more general motion is an ellipse. So you'd go into an elliptical motion. You have to start out in your ellipse right here. But if you slowed down a little bit, you wouldn't go shoot out far enough over here to keep going in a circle. So you'd start heading towards Earth, and then you'd speed up as you went towards Earth, and you'd start going in an elliptical orbit. If you speed up, right? Whoa, not sure what happened there, but this is always an adventure with this thing. If I speed up, I would go into another elliptical orbit. So that one I'm showing in green here. If I went faster than that speed we calculated and I was already at this radius, I would shoot out too far and go into a different ellipse there. So then again, most of the orbits we do, see with satellites that we put in motion, we try to make them pretty much uniform circular motion. That's not to say that everything's like that. That's not to say that every planet going around the sun is exactly a circle. Some of them are more elliptical than others, but surprisingly circular, most of them. Okay. Here's the last question I want to talk about, and this is for the last question on there. How much time, we call that the period, does it take an object to complete one circular orbit? So that capital T is called the period, and that's how much time it takes to go exactly once around. It doesn't have to be a circular orbit. We're going to consider the circular case here. How might I approach that? Yeah. Sure. In fact, let me just work on what we've got here. We've already got a good starting place. Some good cancellations take place. But you're saying that speed is constant. We're in uniform circular motion. So I can use any distance as long as I use the corresponding time. And let me, just so this is in the video, unshare the screen. So we're going to say the speed is equal to any distance divided by the corresponding amount of time, or any time I choose, as long as I use the corresponding distance. And by definition, I want that time to be one period. And so, of course, I go through one circumference distance in that one period, right? So let's put that in up here for our V. I have 2 pi r over t that then needs to be squared. And, you know, there's a little bit of algebra to solve for what t equals, but it's not terribly hard. You're going to have a 4 pi squared r squared over t squared and so on. Let me go back to the slides. Because I probably got that work out how I wanted it. Let's go back here. There we go. How much time? Yes, same free body diagram, plugging in distance over time trick. That's the 2 pi r over t. So after we've done the cancellation, the only thing left on this side was a v squared. And there's our v squared using the distance over time trick. And then taking this equation, the left-hand side and the right-hand side, and solving for t equals, again, that's a formula you're going to see boxed in Giancali. But it's not a formula I ever remember. I just do F net equals ma. Oh, it's simple free body diagram. So if you know how to do that, it's really kind of 2 steps away from F net equals ma. So it's not too bad. Conserves your memory for things that are worthwhile remembering. So I could take the square root of both sides. But notice that we talked about Kepler's laws, and one of them said the following, and we're seeing the same thing now because Kepler's laws are supposed to be just, they're all contained in Newton's law of gravitation and his law of motion. So if we go back to Kepler's third law, his third law said, if you take the square of the orbital period of any planet that's orbiting the sun, divided by the cube of the semi-major axis length, which for circular motion is just the radius. So for our case, we could just justify calling this r. It turns into r for when it's that case. That's going to be the same for any planet in the solar system. Okay, and you can see from Newton's third law, it's telling us how to calculate what this constant is, right? We had all the other numbers that we could plug into here. And in fact, we know what r is in this particular case too. So that, sometimes you can actually save a little bit of time if you remember Kepler's third law. I think there's one homework problem where you're given a certain asteroid and you're given the period of its orbit at a certain radius, and then there's another asteroid at a different radius and you want to know what its orbital period is. You can just, instead of going through Newton's laws, gravitational law and F equals ma, you could just say, well, if it's a constant, if this is for asteroid 1, there's a certain period for asteroid 1 and a radius for asteroid 1. That's going to be equal to a constant, which is the same as the square of the period of asteroid 2 divided by the cube of the radius of asteroid 2. And sometimes, at least in one homework problem, I think you'll find that greatly simplifies your life. You could start with Newton's second law, but I think in that case, I would start with Kepler's third. Okay, so try to do the last part of problem 1. And why not? Because there's one more problem thrown in at the bottom. Just do problem 2 as well. How short would an Earth day have to become for us to feel weightless on the equator? In other words, it's 24 hours now, but if you wanted someone to feel as if they were weightless, they wouldn't be weightless. The Earth is still pulling on them at the same rate, but they wouldn't feel any force upward from the bottom of their feet. They would be floating essentially just above the Earth. How short would an Earth day have to be? Work on that one. And 1E. 1E has to do with this period stuff as well. Okay, so on part E, actually, if you don't start from scratch, you could start from scratch and solve for T and whatever, but we had already solved for V in the previous part. So Arthur would say, don't do the work over again. Use that V you got, set it equal to distance over time, solve for time. It's a little bit less work, given that we had already solved for V there. And the period ends up being 54, 56 seconds, which if you convert to hours is about 1.5 hours, just to make it more sensible that way. So easier for me to understand how big of a time that is. Any questions on that? All right, let's just discuss 2 together. This is something that probably we could have done back in the first batch of stuff that we did in chapter 5. But we can do it with universal gravitation too. How would you begin this problem? What do you think a good starting point is? Free body diagram. Yeah, I mean, pretty much everything we've been doing starts with someone orbiting in a free body diagram. So the idea is, here's Earth. The circular motion in this case is really you're moving around with Earth. So I'm looking down from space. Here's the North Pole right in the middle of me. So the outside circle is the equator, right? And we're watching Earth rotate around. And the idea is there's a person sitting here. I'm going to draw them ridiculously big, mass M. And normally, if it's me standing down on the equator, there are 2 forces on me. There is the gravitational force going towards the center of Earth. And as I can feel right now, it'd be the same way on the equator. Normally, there would be a normal force. And they'd be almost exactly equal. What's an argument for why they couldn't be exactly equal? these two forces. If they were equal, what would I be doing? What would my motion look like? I wouldn't necessarily, I could be standing still, but I also could be just moving in a straight line. In other words, my acceleration would be zero. If the net force on me were truly zero, I wouldn't be accelerating. And to move in a circle, I have to accelerate, right? I know at this instant, my acceleration is in that direction, which means that this force has to be a little bit bigger than that normal force, right? They're going to be almost equal because I'm not rotating around very fast. My centripetal acceleration is really small compared to little g, but they don't exactly balance. Now, let's suppose we have a little dial. A demon can turn it up and slowly make the Earth spin faster and faster. My r is the same. Remember, the required centripetal acceleration is v squared over r. Now, r is not changing. I'm still sitting at the surface of Earth at the equator. But as the demon turns up the dial and spins Earth faster and faster, my v is getting bigger. And so the required acceleration is getting bigger. And therefore, how is my free body diagram going to change in order to make that acceleration bigger?
It's gonna become like I forget the term for it, but it's gonna stop being a perfect circle and it's gonna become like a bigger ellipse or something.
Well, it would. Now, so you're thinking of if I flew off the Earth or something, but let's suppose we speed up the Earth just a little bit. So I'm standing on the equator. I still haven't left the equator. My feet are still stuck to Earth. But so r is the same. I'm still on the equator. Earth's rotating a little bit faster, so v is bigger, and therefore the required acceleration toward the center of Earth is bigger. What's going to change in terms of the forces? Yeah, I've got to get a bigger net force in that direction. Now, is the gravitational force on me going to change? No. Doesn't matter how you're moving. Newton's universal law of gravitation, right? It's universal, applies everywhere to everything. It has nothing in that has to do with how fast you're going. G, m1, m2 over r squared. Neither of the masses are changing. My distance from the center of the Earth isn't changing. Capital G isn't changing. So this force is what it is, but I need a bigger net force in that direction. The only choice is that that normal force has to get smaller if I'm going to have a net force bigger going towards the center of Earth. And the more the demon turns up the speed of rotation of Earth, the smaller that normal force is going to be. And at some critical speed, the net force that I need in order to give the required acceleration at that speed is going to be exactly what the gravitational force is. In other words, no normal force is needed. And at that point, I will feel no pressure up from the bottom of my feet. If I hop up a little bit, I'll be floating just above the surface of Earth. I'll feel in all respects like I'm weightless. One hint of that is that I don't feel any pressure from the bottom of my feet, but I will feel like I'm out, kind of in outer space and weigh nothing. So at that critical speed, this is the free body diagram, just that one force. It's like I'm in orbit, very low Earth orbit, right? You're right at the surface of Earth. I'm 1 inch above Earth and orbiting Earth. And we want to know something about the period, right? How small would an Earth day have to be? So let's use this as our free body diagram. Normal force is gone. At that critical speed, I always take plus x toward the center of the circle, and let's do the sum of the force x components equals max. Only one force x component, g times my mass times the mass of Earth divided by r squared. And in this case, r is the radius of the Earth. If I go to the center of that big sphere, the distance between the two masses is the radius of the Earth that needs to be squared. That's the left-hand side. And that's equal to the mass in the free body diagram. That's my mass. Times ax, that's v squared over r. Let me just leave a little placeholder in there because we know we want the period, the time for one Earth day, right? That's the period of rotation of a point on the equator. So we're immediately going to do the distance over time trick, right? 2 pi, let's see. This is the radius of the circle that you're on, so that's the radius of the Earth. 2 pi times the radius of the Earth is the distance I go by definition in one period. And I just need to solve for t. It's exactly like what we did before. So let's cancel one of these. So we're really redoing the work. And then you got to square that out and solve for t. It's the same t we found before. It's as if I'm in orbit around the Earth. I really am in orbit if I'm floating an inch above Earth. So in this case, I get about 1.4 hours when you plug in the numbers. So it has to, compared to 24 hours, it's been shortened quite a bit, right? We're not close to being weightless, but, if you made it about 1/20th or, a little bit less than that of the current period, that's not a tremendous change. You would feel weightless on the equator. The other question that's related, what about, so imagine we're on the equator, we're going around in a circle, but I want to be able to stand on the ceiling completely upside down and feel normal. Feel like gravity is up. Now we really know gravity is toward the center of Earth, but I want to feel like gravity is up. How fast would we have to go there? Let's just think about the free body diagram, right? So I'm standing on the ceiling and I want to feel my normal weight force going towards the center of Earth, right? That should be the force from the ceiling down on my feet, or yeah, down on my feet. So if I drew a free body diagram at this instant, but let's just draw it over here. Here's me. The force I want coming down from the ceiling is mg. Plus Earth is pulling on me with the same force, mg. So if I'm going to feel normal, I better have, in addition to my normal weight force, a ceiling force down on my feet so I can walk around on the ceiling and feel normal. So if we do the same thing, I'm assuming this is the direction towards the center of Earth. To, instead of writing this big mess, I just wrote mg. That's a simple, if you're at the surface of Earth, that's the easier way to write the gravitational force. 2mg is equal to m times 2 pi r Earth over t squared divided by r. Doesn't matter how heavy you are, it's the same rotational speed, so it's going to work for all of us. And you can solve for t. T is a little bit different there. I don't have it written here, but it looks like it's going to be a factor of square root of, no, divided by 1 over the square root of 2. So it's going to be close to 1 hour, I think. I don't have it in my solutions here, so I can't tell you the exact number there, but it's got to be a little bit shorter in order for you to stand on the ceiling. But kind of a cool trick. Any questions on this? Yes, Sarah. There are two so 1 mg is the usual place it's coming from. Earth is pulling down on me. I'm at the surface of Earth. I'm just standing up on the ceiling. Earth's still pulling down on me toward the center of Earth with strength mg. But if I want to feel normal standing on the ceiling, I'm expecting that my feet up there are feeling a force downward that's equal to my weight force, right? Because normally if I feel normal here, I would say, whatever my weight force is, I expect to feel that same force up on my heels from the ground. When I'm up on the ceiling, I expect to feel it in the downward direction. So Earth's still pulling on me, plus I want the ceiling to be pushing down on me towards the center of Earth too. And those forces I want to be exactly equal in that case. Just a different example. Okay, good. I think that's the end of everything in this chapter. Let's just check. Problem. Yes, yes. Any more questions before we move on to chapter 6 and talk about something sort of completely different? We're going to take a break from free body diagrams for a little bit. other than in the process of deriving some things. So we're going to head into the concept of energy, which you've all heard of before. It's an important concept in physics, but we haven't really defined it yet at all. And we're going to start out, I think, the same way that Giancoli starts out, which is talking about one particular kind of energy transfer, which is called work. And it doesn't necessarily mean the same thing that we mean in everyday language, but it's sort of related, confusingly enough. So let's define work. We're going to imagine that it doesn't matter how it gets there, but there's some object we're going to follow along, and it's moving from an initial position to a final position. And maybe there are lots of forces being applied to it, which are causing it to curve along or something. It doesn't have to be just one force, but we're going to concentrate on one force. There could be other forces, but we're just going to concentrate on one force. And at least to start out with, we're going to assume that force is constant in magnitude and constant in direction on this object as it moves from initial to final. So we might draw it that way. That force is being applied, same direction, same magnitude, everywhere along the path. Okay, I'm just calling it F. Now we're going to break things up into components here, Fx and Fy, and of course I need axes to know what x and y mean. So let me put some axes on there. I chose the obvious ones here, horizontal and vertical as x and y. And now let's break up F into Fx and Fy, right? In my coordinate system, Fx would be positive, Fy would be negative, right? So we just got to conceptually do that or think that we know how to do that. But I'm going to remove those because those sort of clutter up the diagram. So we can compute the x and y components of F. We can also compute the x and y components of the displacement vector. The displacement vector goes from where it started out to where it ended up, right? So I've just defined some initial and some final, and that's what its displacement vector, delta r, looks like in green. And I could break it up into x and y components too, right? Parallel to each of the axes and figure out what they are. All of this is going to go into a definition. The definition is the work done by this force. So the force is doing work on the object as the object moves from initial to final. And the work done in this case, if you needed a z, if something was truly moving in 3 dimensions, you might need an Fz times delta z as well, right? But in this case, it's just moving in 2 dimensions here, so this is enough. The work done is Fx times delta x plus Fy times delta y, and I really have to put in all of the correct signs in there. Fy is going to be negative, delta y is positive in this case, so you've got to think about all those things. Let me pass out a worksheet now, and you're going to try to use this in problem 1. It looks like, oh, before I pass it out, I forgot to mention the unit of work. You can see from the definition, it's got to have units of newtons times meter for SI units. And it's used so often, energy is so important, even that trivial combination gets a shorthand unit of joules. So 1 joule is 1 newton times meter. Okay, and we're going to do exercise 1. It looks like this while I'm passing out, so you can read it. A bird flies from this little perch up here along this crazy path and lands down there. And the question is, how much work does gravity do on the bird? Of course, gravity is not the only force on the bird. Clearly, it's got to be flapping its wings to go on such a crazy path. Otherwise, it would be a parabola or something like that, right? So air resistance and the force on the wings is clearly not negligible here, but we don't care about them. We only want the work done by gravity. They're just going back to that slide if anybody wants to look at it. All right, so you may be doing your calculator work, but let's just solve it together. Here's the picture, roughly speaking. The bird takes off, it does some sort of loop and lands on the ground, but we want the work done by gravity. And we always, because there are multiple forces usually on something as it goes, so it's useful to put a little subscript on here that tells you the work on what object by what force. So I'm going to say the work on the bird. This seems really excessive right now, but we'll find that it's good to get in this habit by gravity. Right, the work is being done on the bird, and gravity is the force we're concerned with. Of course, air is going to be doing some other work on the bird. We don't know about that. Okay, so if I want X components and Y components, I've got to choose some axes. I'm going to choose kind of the obvious ones, horizontal and vertical, plus Y is up. And we're talking about the gravitational force. So isn't the X component of the gravitational force 0? There's the gravitational force on the bird. It's all along the Y direction. So this is 0. I don't really need delta X, but delta X would have been 30 meters. Fy is going to be, well, the magnitude of the gravitational force is m times v, and it's going to be a negative Y component in my coordinate system, right? Minus mass of the bird is what? 0.5 kilograms times 9.8. There's my mg. That's the force. It's a negative Y component. And I need to multiply by delta Y. What's my delta Y here in my coordinate system? Minus 50. It's important that you refer to your coordinate system, minus 50 meters. So the minus signs cancel out when I multiply them together, and I get a positive number, 245 joules. Okay, it is what it is. Not so interesting because we don't have any intuition about joules yet, but that's just running through the definition. Any questions on that one? All right, let's go back here. Yes. Oh, okay. I see. I have my solution on there. Now, you probably don't see this formula appearing in Giancoli, and that's because Giancoli immediately makes a simplifying assumption or a technique for simplifying this formula, and that is, well, you know, it's being displaced in my object example from there to there. I could align my x-axis exactly along the displacement from initial to final, for what I've defined to be initial to final. And then delta y would be 0, right? It would have 0 y displacement between initial and final. And so when I look at that formula, I can just forget about this piece down here. And this is the formula you'll see, I think, in Giancoli when you did the reading, fx times delta x. It assumes you've aligned your axis x with the direction of displacement. But you know, usually that's a good simplifying thing to do. It wouldn't have been so convenient here. Okay, so fx, the interpretation is that's the component of the force that we're trying to compute the work that is done by along the displacement direction, right? We're just going to take the component along the displacement direction. It's almost 0 in this picture. That's just sort of a coincidence. I didn't mean for it to be perpendicular to the displacement, but just how it ended up in my picture I made there. And delta x is the displacement of the point at which the force is applied to the object. Okay, so if we realign things and sort of, you know, I like to have x going horizontally. The object started here, ended up there. There's some constant force being applied to it. We're assuming it's constant right now. And so we can simplify the formula. In fact, this is another formula you'll see in Giancoli. If we know that angle theta there and you know the magnitude of the force, the x component of the force can be calculated as the magnitude of the force times the cosine of theta, right? Just find the x component of the force. That involves a cosine there. Okay, let's look at exercise 2, which has 3 parts to it. A block is being dragged at constant velocity, and that's something you need to pay attention to. It's important for this problem. here's a block just to demonstrate. You're pulling a string at an angle relative to a horizontal table, but you're pulling it at constant velocity, keeping the string at a constant angle and keeping a constant tension in there. And notice if I pull a little bit harder, it would start accelerating. No, we're not doing that. I'm pulling just hard enough to keep it going at constant velocity. That's the setup here. How much work does the string force do on the block during the motion? How much work does the kinetic friction force do on the block during the motion? How much work does the normal force do on the block during the motion? There are 3 different forces. Well, there's more than 3 here, but I'm asking about the works done by 3 different forces. So you might want to draw a free body diagram first just to visualize all those forces we're talking about. So if you want to use that formula on the slide that's up now, you probably want to align your x-axis with the direction of the displacement that is shown for those 2 point whatever meters. Just so you know, if you want to check your work, I get 117.5 joules for A. Okay, I know I'm not giving you enough time to do it all at a leisurely pace, but at least hopefully you've gotten through A, and so you get a taste of how this is going. Some of you, it looks like, have finished in this case. So here's the displacement. I'm going to want to align my x-axis with the displacement direction in order to use that fx delta x simplified formula. So I'm going to choose plus x along the direction of the displacement. And then the force on the string, force by the string is of strength 50 newtons. So its x component is 50 newtons times the cosine of 20 degrees. This x component there, times the x displacement. So you work those out, 117.5 joules. B is asking about the kinetic friction force. There's got to be a kinetic friction force. Otherwise, it would be accelerating as I pulled on it, right? There would be nothing holding it back, but friction sort of balancing out the force in the x direction. So if I do a little free body diagram here showing all four forces that are being exerted on it, there's no acceleration. It's moving at constant speed, constant velocity in this case. So that means acceleration components are all zero. And that means the x component of the string force exactly has to balance out the x component of the friction force. Okay, so if I do F net x equals 0, because it's not accelerating at all, it's moving at constant velocity, that's crucial. That allows me to solve for the magnitude of the friction force. Friction force is pointing to the left in the diagram, strength 46.98 newtons about. And now I'm going to calculate the work done by friction on the block as it moves. Okay, delta x is still 2.5. Friction is pulling on it through that 2.5 meters. But the strength of the friction force, well, I need Fx for friction, and Fx in this case is negative, right? If plus x is to the right, if my plus x is along the direction it's being displaced, then the friction force has a negative x component. You got to put those minus signs in there in order to use this Fx delta x formula correctly. Okay, and it's exactly equal and opposite to the work done by the pulling force, the string force. It's kind of interesting. We'll see how that comes together later. Yeah. Well, in this case, I was just going from this formula right here where there's no cosine of theta. If I did use the cosine theta one, my theta, just to back up to that slide, if this is the direction it's moving, my theta would be 180 degrees. You know what the, right? If I said, how far is that force tipped over? Well, it's tipped over to the left. So that angle theta would open up to 180 degrees. Do you know what a cosine of 180 degrees is? -1. So that's where that minus sign is coming from. You could technically use that formula, but you got to remember the angle is relative to the direction of that it's being displaced. How far do you have to rotate around to get to the force we're concerned with? And in this case, it would be 180. Okay, last question. Whoops, passed over there. How much work does the normal force do on the block? Well, the normal force does 0 work because I need the x component of this force times delta x, and this force has 0 x component in my coordinate system. So it does 0 work, or 0 times 2.5 meters is 0. Okay, so just to sum up, the normal force and the weight force, we didn't do that in this example, they do 0 work because their components along the direction of displacement are 0. The string force does positive work, and the friction force does negative work. And we can sort of figure out exactly when something's going to do positive, a certain force is going to do positive work, negative work, or 0 work. A positive work done by a force means it pushes or pulls more or less along the direction of the motion, right? If the force we're concerned with, the object is moving in this direction, and it doesn't matter what exact direction the force is, but if it's pushing or pulling more or less along the direction of motion, then its x component in this simplified formula will be positive if plus x is the direction it's moving, okay? Negative work means it pushes or pulls more or less opposite the direction of displacement or direction of motion. And 0 work means it pushes or pulls perpendicular to the direction of motion. Oh, okay. So that tells you if you've got a force, if I'm holding this block and I'm concerned with the work done on this block by my hand, and I lower it down like that, initial to final, what is the sign of the work done on this block by my hand? Initial is here, final is down there. 0. Which way is my hand pushing? Up, right? Which way is it being displaced? Down. So it's more or less opposite. To be 0, it would have to be perpendicular, right? This would correspond to me doing 0 work with my hand force, right? My hand is pushing up to hold it, to keep it from going down, right? I'm pushing up with my hand while it's being displaced in the perpendicular direction. So I'm doing 0 work in between any 2 times in that motion. But if I'm pushing in one direction and yet the object is moving in the other direction, that's negative work. Okay, here is, oh, I thought we were over, but the clock's going crazy. We are close. We got time for this voting question. I think didn't I use this for something else earlier? I'm recycling a picture that I hand drew. The 3 kilogram mass slides down a frictionless inclined plane. Which of the following works as negative? So I mean, imagine I held this and then I let it go. It's just accelerating while the string stays taut. Which of the following ones is negative? You have to kind of read and turn it over in your head and as you know, we're imagining initial is an earlier point and it's sliding down the plane and the other one's falling straight down. That's between initial and final. All right, let's just see an initial vote. I don't know if you guys are all ready, but people are sort of rustling around like they might be ready. Let's see. I've got to see which one I'm voting for here. Okay, hold them up if you got them, if you're sure, if you feel confident. Yeah, the B's or 2's have it, and I agree with that one. The work done by the tension force on the 1 kilogram block. The work done by the tension on the 3 kilogram block, well, notice the 3 kilogram block is going down into the right, and the tension force is pulling on it down into the right. When you pull more or less along the direction of displacement, that's a positive work being done on that object. C, the work done by gravity on the 3 kilogram block. Well, let's see. Gravity is pointing downward. The 3 kilogram block is going down and to the left. So gravity is going more or less along the direction it's being displaced, not opposite. It's trying to pull it down the plane. So it's sort of winning out there. That's positive work. Work done by gravity on the 1 kilogram block. The block is going down. Gravity's pulling on it down. That's the hallmark of positive work. So B is the work done by the tension on the 1 kilogram block. Tension's pulling up on the 1 kilogram block while the block goes down. That's the hallmark of negative work. So again, just to do one more example in the last minute, I've got an object here. As I raise this object up, is my hand doing positive, negative, or 0 work? Positive. What about gravity as I raise it up? Negative. What about gravity now? 0. What about gravity as I'm pulling it up like this? Yeah, negative, because gravity is pulling down, which is more or less opposite the displacement. So you can just, I would recommend when you're calculating a work, the first thing you do is figure out the sign. Because a lot of times it's easier then to figure out the magnitude of the work and just throw the sign on it at the end, like kind of like we do for components. So get used to thinking about what is the sign going to be, positive, negative, or 0, and then calculate the number after that.